research to reality webinar series that we started last month. And the aim of that has been what? To be able to consistently put out information every week, which is why we've been having weekly webinars on energy transitions, on energy matters arising. And of course, that's a build up to Smart Research Conference coming up in October. So, as I said, so last week we were privileged to have a distinguished speaker in person of Professor Sam Adaramola from Norwegian University of Life Sciences in Norway. And then he took us through energy transitions in Africa. And before I proceed, I would like to say out that what, for those that are on the call, please make sure to reach out to others because, as I said, we have a distinguished speaker in the house today, just like we had last week, and you would not want to miss out on what he has for us today. So please, if you are here, you can reach out, send a message to one or two, and then let them know that this meeting has started. So, as I said, so in same line also, if you're in the meeting, please make sure to mute yourself. And if you have questions during the course of this webinar, make sure to drop it in the chat box so that it can be attended to. All right. So this week we are moving on to the topic, still in the same research to reality series. We are moving on to the topic, thermal technologies for plug and abandonment of oil and gas wells. I'll take that again. Thermal technologies for plug and abandonment of oil and gas wells. So a question that will come to mind is that why does this matter? Hello, can you hear me? I think I have some issues with my network. Can you people hear me?
Very.
All right. So as I said, so we're talking about what? Thermal technologies for plug and abandonment of oil and gas wells. So historically, we've had it that what industries have relied on placing Portland cement plugs inside the well bores. And over time, these cement barriers fail due to tensile stress from pressure changes in reservoir or prolonged exposure to underground fluids, leading to leaks. And of course, that's why we've had the advancements, of course, and then we've now had thermal technologies. And what's thermal PA? Just a brief introduction before I introduce our speaker. So thermal plug and abandonment is an emerging game-changing approach which uses localized extreme heat to literally melt the well steel casing, the surrounding cement, and the rock formation together, creating a permanent and impermeable plug, which means that the thermal technologies is something that is way more secure than the normal Portland cement plugs that we've been using before now. So, as I said, it is still something that it's coming up because we've been so used to Portland cement for so long. And it is a topic of interest, actually, because as I said, it is something that applies to critically oil wells and all. I'm a chemical engineering student, so I know how that works. In talking about petroleum, talking about oil and gas, this is a very relevant topic in that aspect. So today, to take us through that topic, we have a distinguished guest in our midst, and in the person of what? In the person of Professor Marcelo J.S. de Lemos. Now, who is Professor Lemos? Professor Lemos is a renowned mechanical engineer who currently serves as a full professor at the Aeronautical Institute of Technology in Brazil. At ITA, he is the founder and head of both the Computational Transport Phenomenal Laboratory and the Competence Center for Energy, and he also serves as the head of the Department of Energy. His academic journey includes a bachelor's and master's degree in mechanical engineering from the Pontifical Catholic University of Rio de Janeiro. Following this, he earned his PhD from the Purdue University in the United States. His research expertise is vast, spanning computational thermofluid dynamics, heat and mass transfer, impermeable media, renewable energy systems, and modeling of thermochemical systems. Professor Lemos has made massive contributions to the academic and professional engineering community, publishing over 360 articles alongside several books and book chapters. Most importantly for our discussion today is the author of Thermal Plugging of Oil and Gas Wells, Modeling, Simulation, and Experiment. This groundbreaking reference book details the use of thermal sources and exothermic reactions as cost-effective, efficient, and environmentally friendly solutions for well sealing. Its global impact is recognized through multiple prestigious fellowships. He is a fellow of the American Society of Mechanical Engineers and a fellow of the Royal Aeronautics Society. Additionally, he is also an associate fellow of AIAA and a member of ASTFE. So please join me in welcoming Professor Marcelo de Lemos. So the ground is yours, sir. Thank you very much, sir, for being in this meeting.
Okay, thank you very much for this nice introduction. So, are you guys able to hear me and see me? I guess yes.
Yes, we can, sir.
Okay, good, great. So first of all, I'd like to let me try to share my first slide. Let's see if that thing works. Are you guys, can you guys see my first slide?
Yes, sir.
Okay, good, great. So first of all, I'd like to thank the organizers of this webinar, in particular Professor Emmanuel, and also AJE, the host of this meeting. I'm sorry if I did not pronounce your name correctly. And it's a pleasure indeed to take part in this event. So today we're going to be talking about a little bit about thermal technology for plug and abandonment of oil and gas wells. And I work at the, my name is Marcelo de Lemos, as said by the speaker. And I work at the Aeronautical Institute of Technology in São Paulo, Brazil. And before we go any further, let us first brush up our geography class. We have the map of the world here with three important lines. We have the Tropic of Capricorn that goes through the Gulf of Mexico, island of Cuba. And then we have the equator line dividing the world in half. And then down here we have the Tropic of Capricorn, limiting the so-called tropical region, if you will. And the Tropic of Capricorn is located about 80 miles from ITA, which is the Aeronautical Institute of Technology. So every time that I go from my city to the city of São Paulo to catch a flight on the highway, there is a sign saying that you are now crossing the Tropic of Capricorn. So you're all invited to come and cross the Tropic of Visitors and cross the Tropic of Capricorn if you haven't done so yet. Okay, so the presentation outline is going to be like this. So first of all, I'd like to say a few words about ITA, the origin of this institute, and also our lab, which has the acronym in Portuguese, LCFT, and then move on to the problem of this talk, the idea of a plug and abandonment of wells, and then the use of thermite as a compound, and show some experiments that we have done, go through a mathematical model and show some simulations and try to reach some conclusions. So ITA is an engineering school. We only graduate engineers, and we are located here in the state of São Paulo and the south or west part of the country. And we graduate engineers in the 6 branches of engineering. And down here in Brazil, we have a standard 5-year bachelor program. Right? So everything started back in 1950, right after the Second World War, when a handful of officers from the Brazilian Air Force went up to Cambridge, Massachusetts, and hired 3 or 4 professors from MIT to come down to this country and put in writing a plan for us to have an engineering school of aeronautics that one day would lead us to have an aeronautical industry. Today we have a company called Embraer. We're going to be talking a little bit about it. So in the beginning, we had professors from 12 countries in Brazil, and we had a strong cooperation with American universities and European universities as well, in particular MIT. And our first 4 rectors or presidents, they were Americans. The first president was Professor Richard Smith. At that time, Professor Smith was the head of the aeroastro department at MIT. And then we had 3 more Americans as rectors, and the 5th rector was the first Brazilian, actually, president of the institute. So ITA, as you can imagine, had a very strong technological impact on the technological development of the country. And ITA provided the ground for, in 1969, a group of former ITA students found a company called Embraer, which is the Brazilian aircraft company. And over the last 4 or 5 decades, Embraer has become the 3rd largest commercial aircraft manufacturer. After the 2 big guys, Boeing Group and Airbus Group, which Airbus is European, and as we all know, Boeing is American. So in 2019, after years of negotiations, Boeing and Embraer, they set up a deal of joint efforts, and Boeing was going to buy the commercial aviation part of Embraer, not the military one, not the executive aviation. And the idea was to follow a similar merge that happened in Europe, with Airbus buying a Canadian company called Bombardier. Bombardier manufactures mid-size aircraft as well. So the guys in the Americas said, okay, let's do the same. And because of the pandemic in 2020, and because of the problems with 737 MAX, so Boeing has decided to cancel the agreement, and the 2 companies became again independent companies. This is the latest product also from Embraer. It's a military cargo. They have been selling this to Asia countries and Europe as well, and maybe in the future also in Africa countries. As a matter of fact, Embraer has a footprint in the aviation market in Nigeria. There are 2 companies in your country. It's called Air Peace. They operate these mid-size aircraft, 110, 120 seats, and also United Nigeria as well. So both companies, they have mid-size and small aircraft. So they also, Embraer is also present in the African market, in particular Nigeria market. Okay, talking a little bit about our laboratory. Our laboratory is called the Computational Transport Phenomena Laboratory. It's linked to our Department of Energy in our institute. We started activities back in 1995. Experimentally, in 1999, we became official. We became an official laboratory of ITA. And our mission statement is to support computational activities needed for research and development projects involving numerical solution of flow, heat, and mass transfer problems. And in 2006, we became part of the Petrobras computing network. Petrobras is our national oil and gas company. So in 2018, we inaugurated our new building. So we are a research group in the institute that has the whole building on for us. That was very nice. That was a grant from the oil and gas company. And today we have facilities like an auditorium, meetings room, room for visitors, room for classes and students, collaborators. So as I mentioned in the beginning, you are most welcome to come and visit us, even stay for some time. And if you have not yet crossed the Tropic of Capricorn, please come and visit us. So, talking a little bit about the specific subject of this presentation, what I'm going to be exposing here is somehow a collection of ideas that we have published over the last 5 or 6 years. And we also put together 2 books. There's one book by Springer and the second one by Elsevier. This one was published late last year in December. And that book and those 2 books, they detail a little bit what we're going to be discussing here. So what is the big deal with this plug and abandonment of oil wells business? So let's see. So there's an increasing cost of abandoning wells, and the situation is the following: when an oil or gas field becomes depleted, it's no longer economical to be operated. The oil that it might be even have some oil in there still, but it's not economical to pump it up. So companies decided to shut down the well. And the way they do is they cement. They put a column of cementation. Oh no, a well is a hole on the ground. There's a tube, a large tube, 5 and 8 inches of diameter, and a small tube called the production tube, through which oil comes up. So after the life of this field, companies decide to shut down, and usually it's costing now a little bit over $20 million per well. And if it's an onshore, from $500,000 to $1 million per well, just to do this standard cementation. So cost of abandonment is coming up, is going up, and also the effectiveness and long-term integrity of this abandonment. For you to have an idea, the Norwegian standard says that this operation of abandonment is, let's say, this column of cementation, this column of cement, it has to be guaranteed that for 500 years, there will be no leak on that well. So you can imagine that an engineering constructions that lasts for 5 years, 500 years, is quite a challenge to be coped with. So companies are looking for situations where they can have, let's say, other technologies and cheaper technology and with more reliability. The problem of low commodity price, which is somehow shaken a little bit because of the current let's say events that we are looking at Middle East. So there's a fluctuation of price of oil, but in general, there's a tendency of price of oil coming down, and the population of all the wells are increasing worldwide. So today, when a company opens up and drills a new well, it has to put on paper already how much is going to be the cost of the burial. So because the cost of shutting down in the future is going to be very large. Anyway, so how much would that cost for shutting down all the existing wells that we have? So this is an example of the coast of the west coast of Brazil, which happens to be actually the same situation of the west coast of Africa, including Nigeria, of course. So we have Gulf of Mexico, who have a little bit almost, 5,000 wells. Norwegian continental shelves, nearly 4,000 wells, and UK continental shelves, 4,600 wells. So millions, thousands and thousands of wells to be shut down. And how much would that cost? In the case of the UK continental shelf, until the end of this decade, the estimated cost for sealing all those wells is about 20 billion pounds, not US dollars, pounds. And in the case of Brazil, we have an estimate of $10 billion for shutting down all the wells that eventually one day are going to be shut down. So companies are looking for different technologies that can reduce this price, that can increase the reliability, and they can provide integrity along the centuries to come. So this is an idea. This is a schematic of an oil well. So an oil well, it looks like a telescope. As you go further down, the diameter of the tube is decreasing. And what the standards say that you have to have two independent sealing positions to guarantee that there will be no leak in the centers to come. And this is the standard way of doing the sealing, of handling the sealing. So the idea of this talk is to present to you a new technology which involves the use of thermite. So thermite is a mixture of a metal oxide and aluminum powder that it's a powder. So once you ignite, it starts a self-propagating reaction with the release of a tremendous amount of heat. So this is not a new reaction. This has been around. It was discovered back in 1893 by a German fellow called Hans Goldschmidt. And the first application for that industrial commercial application was for welding of train tracks in Germany, in Essen. So what is new is to use this old idea in a new application for sealing the well. So the whole idea is to put this material in a well, and patents have been applied in the United States and also in Europe by companies. Companies are looking at how to develop this technology. So patents have been applied, and the whole idea is to put this material inside the well, ignite it, and then with this tremendous amount of heat, you melt everything around. And after the cool down process, you have a block of solid metal, in this particular case, iron. So the basic reaction of thermite is like this: iron oxide plus aluminum powder. It gives aluminum oxide, and pure iron, right? And as I mentioned, this reaction is a self-propagating reaction. It releases a tremendous amount of heat. And the whole idea is with this heat, you can melt everything that is around the well, and then at the end form a solid block of impermeable metal, if you will. So there are different routes for using this particular material. The first one is called the rock-to-rock, which means that once you remove the smaller tubes, the so-called production tubing, you fill up the entire casing with this powder, this material, and then ignite, and then form a block and get something like this, right? The other idea is instead of taking this internal tubing out with it's a big chunk of the overall cost, because it costs a lot of money to go offshore and pull that thing out. Instead of pulling the internal tubing, to use thermite either inside the small tube, the production tubing, and also around the annular section. And the third idea is to search for an intermediate solution, would be the following. So the idea is to destruct part of the internal tubing, the production tubing, melt this, let's say, I don't know, 10, 15 meters section of this, and then proceed with the cementation. Even so, even using this intermediate solution, it saves a lot of money, because the whole idea is to decrease the amount of time that's necessary for the overall sealing. Okay, so we decided to run experiments to first understand a little bit how this reaction occurs, observe the experiments, and see if we could come up with some nice mathematical model that could, for example, lead us to set up a computational platform for designing systems using this particular technology. So we set up a few tests that we call it small scale tests. And our intention is to investigate if we could control the reaction. We have to accelerate or decelerate the reaction, calculate the levels of temperatures that we would get, and see if this amount of heat is sufficient for melting the whole thing around. So a more complete equation for that is when you include more aluminum than necessary, then the stoichiometric ratio needs. And when you include more alumina than necessary. So the whole idea is to investigate if we could accelerate the reaction or decelerate the reaction. So we ran a few tests, small scale tests. And we compare the situation with the stoichiometric ratio and with the 10% more aluminum than needed. And we saw that, we observed that if you put more aluminum than necessary, the reaction is quite violent, and it happens a lot faster. Then we plot the peak temperature in both cases, let's say for a stoichiometric situation and the aluminum-rich mixture. And see, we also measure that the burning velocity, it's very high when we have more aluminum than needed, and it's low when we run a stoichiometric mixture. And also the dispersed mass, the mass that is ejected at the top of the tube, is higher with aluminum-rich and it's smaller when you have a stoichiometric reactor. So we started to understand a little bit how things work. And then we move on with the aluminum-rich situation. Now, alumina-rich situation. So we have again on the left the stoichiometric situation, and on the right the alumina-rich situation. So we compare the two situations, and at the end we observe that if we put more alumina than needed, we decelerate the reaction. So burning takes a little bit longer instead of going faster when we use it before the more aluminum than needed. Okay, so again, we compare our results. So we see here as we increase the amount of alumina in the original mixture. After a certain value, we decrease the temperature level. And also we keep decreasing the speed of the front of the reaction. And also the dispersed mass, the mass that comes out of the tube. And if we put more than 35%, 40%, of alumina, we don't even ignite the mixture. Okay, so there is a limit for the amount of alumina that we can put. Okay, so we move ahead and decided to run a second set of tests, and we call this a medium scale set of experiments. And in this particular case, so the specimen is a little bit longer and larger. In this case, we only use the stoichiometric and compare the stoichiometric mixture with the alumina-rich mixture. Then we ran experiments, again showing the stoichiometric and showing the alumina-rich, comparing both. And again, we had the same behavior of decelerating the reaction. So the burning of the mixture, when we have more alumina than needed, it's slower. So we slow the process. And this is very important because once we have that mixture inside our oil well, we have to be able to control it. If I go faster, go slower, because each well is different from another one, the other one. So these mixtures could be, for example, custom tailored for each field, if you will. So, and then we compare, because in this particular case, we measured the temperatures a long time. So we compared the temperatures, and we had 3 thermocouples. Thermocouple 1 at the top of the, more or less, at the top of the mixture, thermocouple 2 and 3, and here we have the temperatures a long time for the 2 situations. For the 0% diluted or stoichiometric, which is the blue lines, and for the diluted mixture, which is 20% dilution with alumina. So we got this behavior. So our idea is, can we reproduce this in a model, in a mathematical model, and do some simulations? So we got these temperatures with time. So, and again, we compared our experiments. In blue here on the left, we have peak temperatures for all the 3 thermocouples. They are higher for stoichiometric, they are lower for the 20% dilution with alumina. Burning velocity is the same. Burning velocity is higher when you have stoichiometric situation, and slower when you have a diluted mixture, and dispersed mass as well. So these experiments, they agree with the first set of experiments that we had before. Okay, so we started to think about how to model this behavior, and then we have our equation again. So in this equation, we included the equivalence ratio, which indicates the amount of excess aluminum that we have, and we have the excess, which is given by phi, and psi gives us the excess alumina for decelerating the reaction. And for the stoichiometric situation, as we mentioned earlier, we have phi equal to 1 and psi equal to 0. So the whole idea is our model should be able to represent what we had in the experiments if we have more alumina or if we have more alumina. Then we start modeling or putting together a model for simulating the second set of experiments, where we have the 3 thermocouples. And then in our model, we use an axisymmetric situation. So temperatures did not vary with the tangential direction, only with radial direction and the axial direction. So we assume all the boundary conditions, the symmetry line, also the convection irradiation that expelled, if you will, at the boundary, and also the amount of energy that is expelled at the top. because of this mass ejection that we had, conduction also through the tubing, the metal tubing. And then once we had the geometry, and then we had computational mesh, and then we went to calculate the mixtures, properties of the mixture. So in the beginning, first of all, we can have two types of situations. We can have here a mixture that is very compact and there's no gas trapped in between the grains, or you have some gas trapped between the aluminum grain and the iron oxide grain. In this case, we can define a porosity of the mixture. If it is fully compacted, we have the maximum density possible with porosity equal to 0. And then we for each one of these 4 species, if you will, we have a mass fraction that can be defined. We have a volume fraction that can be defined. We have a density of the mixture. Density of the mixture is going to be used in the energy equation. And we have the mass concentration for each species. Remember, we have 4 species. And then we can calculate the thermal conductivity also for the mixture, the whole mixture, and at the end, the specific heat also for the mixture. So properties of the mixture are going to be used in the energy equation for solving for temperature. Okay, so our thermite reaction is like this. So we have 4 components, A, B, C, D, and then we have our heat transfer model. So we have the energy equation written for a 2-dimensional situation, axis symmetric. So we have temperatures varying with axial direction and also with radial direction. And we have the source term. So there's a heat released by the thermal, by the reaction, the chemical reaction. So that release of heat is included in the heat transfer equation as a source term. And then we have the mass transfer for each individual I, each of one of those 4 chemical species. And this last term here is the R sub I, is the rate of which there is a consumption or a production of that particular species. For example, in the beginning, you had only iron oxide and aluminum. At the end, we won't have that. So for iron oxide and aluminum, this guy is a negative number. There's a consumption, right? For alumina and for pure iron, this number is a positive number because there's going to be production of that particular species. And for that particular rate of consumption or production, we use the Arrhenius sort of modeling. Okay, so looking at the chemical kinetics of this reaction. So in chemical kinetics, we have an interesting and very important number called the extension of reaction, with eta. Extension of reaction, it's a property that indicates how much of the reaction is already completed. So before the reaction, eta is equal to 0, as you can see in the picture. Along the reaction, eta increases up to 1. Eta equal to 1 means the reaction is done already. And during the reaction, as you can imagine, the temperature goes up because there is a release of heat. And this particular rate of production of heat is increasing as well during the reaction. So before the reaction and after the reaction, R dot sub K is 0 because there's no reaction. So one important, very important, let's say, assumptions that we made to facilitate the computation of this complex simulation was to assume that there is no transport of the chemical species. If, let's say, there's no diffusion or there's no convection or diffusion in the transport equation. So the time rate of the any value of the concentration of any species as a function of time is solely dictated by the rate at which it is consumed or it is produced, not because it is transported. And then at the end, we used the first order kinetics. So this is also a simplification of a chemical reaction. So we use the first order kinetics. In this particular case, there is a value called n. There's a property called n, which says n equal 1 is the first order. It means a first order kinetic. So that facilitates, those assumptions facilitate convergence of the solution. Okay, so we set up a code. We put together a CFD code with these ideas. And we ran our code and compare it with our experiments that we had before. And for the first case here, here we have on the left, we have the 0% dilution. And we can see that temperatures are higher at the center if we compare with the 20% dilution. So temperatures are lower. And that also reflects the experiments that we had. And then we compare for the 0% dilution or stoichiometric situation. We compare the mean experimental value for the 3 thermocouples and also the mean numerical value. Mean numerical because we had some sort of uncertainty when the reaction started. So we did more than one calculation. We did a few calculations and took a measure and took a mean value to compare with the mean value of the measurements. And you see here that the difference is 5% for thermocouple 1, 1% for thermocouple 2 in the middle, 6% for thermocouple 3. And then we did the same comparison for the 20% dilution. When you have more alumina, when we decelerate the reaction. And again, we compare the mean experimental values that we had from our experiments with the mean numerical value. And again, we had 4% for thermocouple 1, 1% for thermocouple 2, and 9% for thermocouple 3. So when we first sent those results for publication, we sent this to be published, and one of the reviewers of the paper gave us a feedback, which was very interesting. He or she said that, well, I don't believe in those results because they are too good to be true. And then we took that as a compliment, as a matter of fact. So we then explained exactly how the measurements were done, how the computation was done. And eventually, this guy was convinced that the paper was published. And here's a comparison of the temperatures a long time, because we measured that temperatures a long time, for the 3 thermocouples, P1, P2, and P3, for the 2 cases that we measured and simulated for the stoichiometric, and also for the case with addition of dilution of using alumina, 20% alumina. And here in those figures, we have the 3 experiments that we ran. For each experiment, we ran 3 cases of the same experiments to get reproducibility. And then we had also the computation. So we see that the overall, regardless of the situation, if it's 100% stoichiometric or it has a dilution. Regardless of that, for the 3 thermocouples, results are quite good. So this is an indication that somehow the model that we put together is not too far away from reality. So it can be, let's say, improved, of course, it can be improved, but at least we got some results that are quite close to the experimental value. So we observe the reality, we run experiments, and then we model that, we try to model that reality. This is different from getting a commercial code where models are there that we don't know exactly who put it there and how are they, and try to simulate some reality. And we don't know if this commercial code, has exactly represents exactly that reality that we are looking at the experiments. So, for concluding our short talk, so we have seen that this reaction looks like a promising candidate for DNA process because these materials, they are cheap, quite cheap, compared with other materials, more, let's say, another process also being used for sealing the wells. So we figured that alumina dilution decreased the burning velocity and masses injection, and dilution more than 20% did not present aluminum vaporization. This particular, I did not show a picture showing that, but depending on the amount of aluminum that you have, when temperature goes very, very high, aluminum vaporizes. So it melts and then vaporizes. And more than 40%, there's not even propagation. So we prepare those mixtures with a solvent-based preparation. Also, it's not shown here in detail. But if you use a solvent to put together the grains, the connection between the grains is much better than with a dry mixture, if you will. So the reaction generates more heat. And then one of the things that we also did is we used a simplified concentrate model also comparing. And because that facilitates quite a bit numerical convergences. So in this particular case, we have to use at least 10 to the minus 3 seconds as a time step to get the correct numbers for temperature. So with that slide, I guess I conclude this talk. And I'd like to also to pay tribute to my former students, Roberta, Fernando, Casiani, Gabriel, Fabrizio. They all got their PhDs in this with these projects. They have all graduated. They have worked quite hard. And I would like also to thank our sponsors. CNPq is the National Council for Research in Brazil. CAPES is also a funding agency under the Ministry of Education, and CNPq is under the Ministry of Science and Technology. FAPESP is São Paulo State Research Foundation. And Petrobras is the oil and gas company also that contribute with funding on the initial part of this project, and also, as I mentioned to you in the beginning of the presentation, the building that we have. So the new laboratory was also a grant from Petrobras. So now we are looking for new partnerships, for new investments, if you will, from companies that wanted to develop new technologies. So we are open to let's say discussions with interested people, interested students, interested companies that want to come and talk to us, and we'll be delighted to interact with institutions in Nigeria, have students, cooperate with companies. And with that, I thank you very much. Thank you all. And I conclude my talk. So thank you very much. I really appreciate it. Is that okay? Ajaya?
Very okay, sir.
Thank you very much, Professor Marcello, for that wonderful presentation. So before I allow Ajayi to continue the moderation, I want to emphasize that the presentation has so much. For example, like look at this. Who can imagine that plug and abandonment research work can produce, like I can see it here, 5 PhDs, just a single topic, has produced, so which is just very much an encouragement to what we do at the Zero Emission Research Facility, which is very, very much younger than PTA, so it's an encouragement to really see that what we have started can also, just a single problem can produce many PhD, so that's the encouragement of consistency, to look at the problem and the research work continued, and you can see a lot of improvement that you can bring to that. But as we try to wait for question for you, I just want to link up what you're doing here now, what you have just presented, with what some of the participants in the webinar has put forward in the series when we started. In one of the series, there was someone that looking at energy transition precisely, and I'm trying to really link up this with this problem of plug and abandonment of oil well. Someone brought up the need for carbon sequestration, so CO2 sequestration, and I believe that you should be far more knowledgeable with how that kind of align with the process of plugging, and drilling and then trying to sequestrize CO2. So my concern is, as I look at what you're doing in terms of the termite for using both e-transfer and mass transfer phenomenon, is there a possibility that a mass transfer of a carbon sequestration can actually be modeled along the termite equations as you have, so that if that is possible, an improvement over, I know the work you're doing that you're presented is already patented, but of course patent can also be can be improved. You can have an improved patent. So is this something that you're using to not just solve plugging a oil well, as a problem, but solving a problem of trying to improve energy transition challenge of CO2 emissions, and then you want to try to sequestrize CO2 along with the plugging of a oil well. So that's just what was coming in my head. I said, let me put that across to you, but you can think of that, to respond, or maybe wait until when all the audience has their question.
Well, the problem of carbon capture and sequestration could be linked to this technology for the idea of, let's say you have a reservoir, we have some space in there, so you can put the CO2 down there, and then you seal the reservoir, you seal the well. So this could be a link, if you will. But and as a matter of fact, we do have a project on carbon sequestration together with the University of São Paulo, another university. This project just started, and we are still in the beginning. So we are still trying to understand a little bit the key factors that needed. So one of the things is the characterization of the reservoir. If you're going to put, the CO2 sequestrated down there, so there has to be enough room in the reservoir. There are economic factors as well. So CCS is definitely linked to the idea of depleted fields, right? Where you can inject CO2 in situations where you have, let's say, another use for a depleted oil. Yes, this could be done. And this actually has been done. And this technology could be used for economically, if you will, seal the sequestered carbon inside the reservoir. Yeah, that could be a link, exactly.
Okay, thank you very much. So, Israel Ajayi, can you take it up? Your moderation. Isaac, sorry.
Isaiah, yeah. I don't. Am I still sharing my screen?
Yes.
I don't know how to.
You're still on. This is supposed to be a question.
To take it off. This is the first time I'm using Zoom, as a matter of fact. So I had to set it up. So we usually don't use Zoom. So now I'm sharing the screen, but I don't know how to stop.
No. This is still a question. You are still on. This section is a question and answer, so your screen can still be on. You're still we are supposed. I'm just waiting for the moderator to coordinate the question and Q&A section. So your screen still need to be on.
Okay.
So we're just waiting for the moderator.
But something interesting is that we have the west coast of Brazil, where we found this large reservoir that we call the pre-salt reservoir. It's under the salt layer, so we call it pre-salt. So you guys have the same geology. It's the same geology. So if you look at your west coast, you have also a large reservoir of oil and gas. So whatever technology is developing from our side could be applied to your side as well.
Yeah, definitely. And then, as you have actually put forward in the beginning of your presentation, you have, I think Petrobras also operate in Nigeria. And then we have some companies, as you have rightly mentioned. I am not in oil and gas, and I expect the audience that are in oil and gas can actually ask you some practical questions. But definitely Nigeria is a very oil and gas country, and what you do at ITA will definitely be of relevance to the problem in Nigeria. So I'm just waiting for those that are in the know and that want to ask questions to bring their question up. So if there's any question from audience, I don't know if Isaac is having issues with taking the sections as a moderator or no. So let's put up our hands, so that that can be coordinated.
So I want to take up the question aspect of things. I trust that we all can get me on our respective end. So this is the point where we get to ask our moderator question as regarding the presentation we all have collectively listened to. So while we are with the moderators, questions from the audience or from people that are listening in the background, I have a question personally to ask the speaker. So first of all, Professor Marcelo, I'd like to say a big thank you for the contribution of knowledge which you've impacted us with this afternoon. But I have a very quick question, which is one that bothers me. I saw that the question is, why is there a need for plugging of wells, right? Why do we need to block existing wells? Because I saw there is a preferential treatment towards shallow wells rather than deep well. But in the long run, why do we need to block this well? Don't this crude? Are they not like in my country here? Crude is one of our source of financing. So this crude, are they not like necessary? Are they not important? Why do we need to watch? Why do we need to block these wells in the long run? Though, and when we now block this well, will the effect be permanent or is it reversible at any point in time? So that's the question, sir.
So I'm having some trouble with the sound. The sound is kind of flicking a little bit. So if I well understood, so the question is why there's a need for sealing wells. Is that right?
Yes, sir. Yes,
Okay. Today, because of extreme environmental regulations, a company cannot just leave a hole on the ground because there might be leak. If there's a leak, there might be an impact in the environment. In the beginning, you know, a century ago, companies in Pennsylvania, in the United States, they would just leave a hole on the ground. Nobody would care, but you cannot do this any longer. So companies, they are obliged to seal the well, and there are very stringent environmental regulations. For example, I mentioned the Norwegian standard. They require that whatever you do for sealing a well has to be has to be perfect, if you will, 500 years later. So no engineering work can be guaranteed for 500 years, except, okay, maybe the roads built by the Romans centuries ago, they are still on, but most engineering constructions today cannot be guaranteed that they're going to be intact 500 years from now. So there are stringent environmental regulations. So companies, they have to cope with that. And this is why today, what they do today is they do this cementation. So they have a column of 100 feet long cement. And the cement that they use is not the same cement that we use to build our houses. It's a different type of cement. Anyway, so there is this worry about environmental protection, leaks, eventual leaks of some time, accommodation of the soil, whatever. So the companies are investing a lot of efforts in order to develop solutions that are cheaper, because they do have a solution today, but cost a lot of money and time, and so the whole industry is looking for situations of alternative technology for bringing down costs and also raising the reliability of the sealing. So the point is, once the well is no longer functional, there's no more oil in there, or the oil that is in there has no, let's say, it won't be profitable to bring it up. So companies have to seal the well. And even today, some companies, they keep the well open and operational. They do not seal it, even if there's no oil in there, because the cost is too high. So see, they cannot just abandon and leave a hole on the ground or a hole on the bottom of the sea because of potential leak. So this is why even more the need for reliable sealing is being is driving this let's say this search for new technologies that are cheaper and more reliable. So sealing the well in a reliable and fashion is something that from now on is going to be even more important. Okay. I don't know if I answered your question or not.
Yeah, very well, sir. Very well, sir. Very well, sir. So my next question is, after a well has been sealed, I guess its economical value stops at that point.
What was it? The economic, again, your sound is kind of flicking.
Okay, I'm coming. I'll do something now.
So it's about the
now.
economic.
Can you hear me now, sir?
Now it's a little better. Yeah.
All right. So I said that after a well has been sealed, does its economical value stop at that point of sealing? Meaning that you must have spent money to seal the well. So how do they get that money back? Because I know here we are trying to protect the environmental impact of leakages and all. But once the sealing has been done, then the well is no more suitable to be called a well anymore, I guess.
That's correct. Once the field is depleted and they have to seal it, they stop profiting. That's for sure.
Oh.
But sealing is also done. Sealing is also done temporarily. Some companies, they for example, they have a strategic, let's say, thinking in, let's say, saving that particular field that still has some oil, but they do not want to exploit that now, maybe 10 years from now. So what they do a temporary sealing. This is also possible. So sealing is not always done because there is no more oil in there. Sealing is done also because companies, they have a strategy of saving that field for some future, some near future. So this is also existing. Yeah.
All right, sir. Thank you very much, sir. Thank you very much, sir. Okay, so everyone, please, this is the point where we get to ask the speaker a question if we have any question on our respective end. So I'm going to give us a feel of about 2 minutes while I give the floor to Dr. Gedegbe. If there's anything you'd like to mention before we come to the closure of the meeting, of the webinar, sorry.
Okay, thank you very much, Oduayo. And I just want to echo the moderator's appreciation of Professor Marcello for coming on SMART live webinar today. He's been a very good friend. We always meet on a yearly basis at the AIAA event. Although he pleaded to be absent this year. But last year was the last time I saw him, last January. And I hope he's going to be around next January. We've been in the same committee of terrestrial energy committee of the Energy System Committee, Technical Committee of the AIAA, and that is been a very great contributor. And I think last year he nominated me for the associate fellow of the AIAA, and I was so delighted that he chose to do that. Although I'm still waiting for AIAA to announce their decision of the nomination this very year. So it's been a very good committee and wonderful opportunity to connect with different people and all the network that I have across the globe. Mostly, it is that same committee that we get to see different people from different parts of the world. So you are very much welcome to SMART environment. It's just a little bit of trying to mimic what AIAA is doing globally in Nigeria, and trying to grow that contribution so that people that don't have the privilege, because going to America every year is not cheap, from Lagos, Nigeria. It costs a lot of millions of Nigerian currency, to just go and return. And we just find out that when we have a platform like Smart like this, we get to have a lot of people to come around that can benefit from the resources of experts like Professor Marcelo speaking to them. So I say that to say that even though I'm scratching my head how I can bring in some of our work in terms of collaboration to you, which is what I've been doing with other speakers, that their area of work and contribution has been very much directly related to what we do with energy transition. So when we're able to agree on that, then that will give the opportunity for me to invite Professor Marcelo to physically come to Lagos. So I look forward to that possibility, so that even though you will rightly say that you want me to come to Brazil, which I am very much open, and I can tell you that it might be very soon, but I can't tell exactly when that will be now. But it's a beauty that we have, that we can move around and really see what we are doing, and impart and make contributions to that. So thank you very much, Professor Marcelo.
My pleasure, man.
Mm-hmm. So I also want to announce that in the absence of questions, although the moderator is going to let us know if there's any question more for Professor Marcelo. Normally, we would will let the participants know that next week what we will be looking at, and luckily we have an agreement of who will be coming next week already. So he will be speaking on technology-enabled sanitation and water quality management. This was a worker. He has some experience going to the community and impact. And just as we know, the series that we are looking at in live webinar is just about addressing community problems. Based on the research we do in the laboratory, we've been able to go out to the community and solve the problem. So today we have listened to the problem of plugging an oil well that have been abandoned. To next week we will be looking at something more on environmental as well, and quality management and all that. So that's a prof from South Alabama will be our speaker for next week. So that's just the announcement I have for participants now. So back to you, moderator.
All right, sir. Thank you very much, sir, for that. So, Professor Marcelo, just one more question from my end. And okay, during the course of speaking, you spoke about how that cementing, despite apart from the costs associated to cementing these oil wells, there's also the part of they being vulnerable to leaks over time. So how then does the durability of a termite melted rock and steel plug compare? Like when we now have it exposed to highly corrosive reservoir fluids over decades. Did you get that, sir?
Well, I'm sorry, I was not able to, your sound was also kind of some kind of difficult to hear. Could you just say it again, the question?
Okay, sir. I said that we have issues with leaks over time when it comes to cementing these oil wells. That how does the durability of a termite melted rock and steel plug compare when exposed to highly corrosive reservoir fluids over decades?
Oh, yeah. So there are questions about use of this technology in the long term. You are right, absolutely right. We don't know yet. This is why we are still in the investigation, let's say, step, right? But there is a long way to actually get this technology mature and reliable for use. because as you saw, one of the results is a block of fire. And in the well, you can find all sorts of chemicals that might corrode this block of metal, might interact. And there is also a problem that I did not mention. When we have this large amount of heat being generated inside the well, okay, we melt everything around, but we create a stress field, a thermal stress field in the rock around the well. And this thermal stress field may produce cracks. So we solve the problem in the well, and we create another problem around the well through cracks that goes around and oil and gas can leak. So people are still investigating technologies or materials and processes that will minimize the amount of heat that goes outside, or the gradient of temperature. Because if you have a gradient of temperature on the cap rock, the rock that is around the well, so you might induce some cracks due to thermal stresses, as I said. So there are problems. There are problems with this technology that are still being investigated. So we intend to pursue this further, but for pursuing this further, we need to get, of course, more funding from institutions, companies, etc., so we can run more experiments, do some more tests for guaranteeing that there won't be any crack around the well, and that we have a, let's say, a long-term solution in front of us. But you are absolutely right that there are things that are still being considered as the chemical corrosion, for example, because as you said, inside the well, there are several chemicals there that may interact with this material that we put in there. So we still have a path to follow, if you will. So, yes, but we are, at least we are in the beginning. We are in the beginning. Okay.
All right. Thank you very much for that, sir. And I would like to say a very big thank you, sir, for participating, for being a speaker today in today's webinar. We are really grateful for the privilege you've given to us to be part of what we are doing. So thank you very much, sir. And I would like to say a big thank you also to everyone that participated in today's webinar. And as I said, it's a weekly webinar, and would like to have everyone that was part of it today have you all again next week. And in subsequent weeks, of course, I'm building up eventually to the Smart Research Conference coming up in October. All right, so in the absence of that, we've come to the end of today's meeting. Thank you very much, Professor Marcelo, and thank you very much for everyone that's present.
My pleasure. My pleasure.
All right, so bye, sir,
Bye-bye.
and bye, everyone.
Bye-bye.